Okay, so let's start today's lecture. Maybe, uh, I think we can wait 2 or 3 minutes more because I think more students will come today. Okay, so let's start today's lecture. Welcome to join this course, Probability, Statistics, and Machine Learning for Engineers. Basically, same as other courses, we have a 30 weeks class for this lecture. And the first half from week 1 and week 6, I will teach. And then second part, the week 7 to week 11, Professor Marway will teach about it. So the title is probability, statistics, and machine learning. So the first half is going to be about the probability and statistics by me, and the second part about the machine learning is by the Professor Maury. Okay, so every information you can check. Sorry, you can check in on your the teaching plan on the blackboard there. And then basically, this is the tentative schedule. So in each Wednesday, this time at this classroom, and then week 1 to week 6, I will teach about some statistics and probability models. And then week 7 to week 11, it will be about the machine learning. And the last 2 weeks, it will be about the project presentation. Okay, so let me start one by one. Then here this equation. Okay, so the objective of this course is to introduce a broad range of the statistical and machine learning method for civil engineering applications and to equip students with the knowledge of applying the skills learned to quantitatively model and solve real-world problems in civil engineering. So intended learning outcomes appreciate the need for quantitative approach for modeling based on mathematics, of course, and to understand the conceptual models, conceptual foundations of probabilistic and statistical models, and also to understand the mathematical foundation of different type of machine learning method, and demonstrate the capability to quantitably model and solve real-world engineering problems. Before I start, so if I understand correctly, most of you are from CEE, right? Or is there any other major? Well, as joint maybe. Could you tell me what is your major?
From BRE.
BRE, okay.
AP.
AP, okay. AE, okay. Okay, and RA, okay. Okay. Okay, so it's quite broad. Okay. Okay, I see. For the assessment, this is the PhD course, so we don't have any final exam. But instead, to evaluate your performance, we will have two quiz, and two homework assignments, and final project. Okay, so especially for the final project, it will be about your own work, your own anything about your PhD work. But considering the topic and the title of this lecture, it should be something about probability or statistics or machine learning, whatever. Okay, so I mean it's an individual project, so you don't need to learn much. So it will be a presentation will be only 5 minutes. So it means that you don't have much time. So because me and Professor Mari, we are both in the transportation engineering in CEE. So our knowledge is based on transportation field. So when you present something for your presentation, I mean your how to say major specific information. I mean, it's not our point. Our point for evaluation, how you actually use the probability, statistics, or machine learning in your own work. That's the focus for this 5 minutes. So you don't need to explain, oh, my work is about blah, 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 blah. For instance, environmental engineering, so this is the environmental issue, blah, blah. It's okay. We will emphasize about the probability, statistics, or machine learning, whatever. Okay. Also, for this project presentation, summit deadline is the April 16th. So maybe later for the second half, Professor Mao will also emphasize it again. Okay. So also same, I mean, for the evaluation, you project report, focusing on the method. I mean, how you use the probability or statistics or machine learning, and why you use it. That's the main point for your evaluation. Okay. So other things are okay. So any question? Any question about this course? So some question or some? Oh, yes.
For the second assignment, I noticed that it got a report or something.
Sorry. Second assignment. Yes.
It's just in your slides.
My slides. Okay.
And yeah,
This one. Yeah.
And for the assignments, it's also something that's related to our major. That's kind
in your lecture, it's about probability statistics and some mathematical problems or some, yeah. Any other question? Okay, so this is the general information, and then reading risk and references here. And before I start, because I'm in the transportation engineering, maybe my lecture, the topic itself is more general statistical and probability models. But sometimes if I use some examples, maybe it will be about transportation because it's my expertise. I will try to use some more general examples, but it can be incorrect for other domains. So maybe my explanation about the examples, maybe more about the transportation field. Okay, and that's all. So today is the first lecture. So I will move overview. I mean, today the content is not heavy, so maybe from next week it will be more specific. Okay. So if I just correctly, I heard that the PhD students here, they are all the very good, very expertise in the statistics and mathematics. So I think the basic information you already very expertise, right? So today I will my lecture will be some overview, so it may not new for you. But if you feel some difficulty in terms of mathematics today, then I recommend to the class is not suitable for you. If you think that today lecture content is too difficult, okay? So today is very overview, okay? Okay, so here I basically make some explanation based on the civil engineering domain. So why is statistics and probability necessary in civil engineering? Because the statistics and probability are both absolutely fundamental in civil engineering. So statistics determines power, and probability in statistics, and uncertainty and certainty, blah, blah, blah. So I try to arrange the application, the examples of the statistics and probability in civil engineering here, something like that. So some environmental engineering, also geotechnical engineering, structural engineering, hydrogen engineering, and so on. So most of your research work in PU based strongly related to this mathematical issue. Okay, so before I start, maybe let me briefly explain some more over. So if I assume correctly, maybe most of you, I cannot say all, but most of you may use the data, right? Some data from your experiment, data from survey, or data from whatever. Maybe your major work could be data analysis, right? So how you get the data, maybe it's different for your major, right? So in the data, let's assume data there. The information may be different, but normally there are several variables, blah, 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 blah. Blah, 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 right? So this is the general form of your data for your PhD work. So in here, what we will do is that we choose one for our focus. Why? If something, I mean, it depends on your topic, whatever. And then we make a model like something like that. Any statistical, econometric, or some probability model, whatever. Here. So the focus of this lecture is that how we can get the F here. This is the purpose of the first part. But of course, recent days, how to say, with the rising of the machine learning is a little bit different. F is a function here. So y equal f, x here is the vector. But in machine learning case, how to say, f is unclear. Because the machine learning, they have no strict structure. Okay, so of course, I mean, this relationship has a pros and cons there. So in the machine learning model, it's very flexible. So it's very good for the prediction or model fit in general. It's much better because we have a strict F. So it means that we feed the data into the certain F, right? So if the data does not strictly follow the F, we just make a match with this function. So this is the classical approach in the statistics and the probability models. But machine learning model, they have no structure. So they just run the data relationship itself. So it's quite flexible. So prediction power model fit is better than classical way. But what is the worst there? Then interpretation. Okay. So from here, we normally, for instance, just thinking about the general regression model, we have blah, blah, right? And then here, what we can get from the regression model, for instance, we can get the beta, right? The estimation. And then using the beta, we can make some more policy discussion or some further sensitivity analysis, whatever. Okay, so interpretation is much better in the classical approach. So it's the pros and cons of them. Okay, so and then so focusing on my part, the first part in the probability and the econometric model. So what is the issue at the PhD level? So I have a regression model, so I can use it. That's all. Then why you need to learn more? Because the type of Y is different over U. Statistically, sometimes it's a continuous, sometimes it's discrete, and sometimes it's a mixture of the continuous and discrete together, right? Also, X is also can be different. Some of the variables can be countable, but some of the X is uncountable. Even some of the X is measurable, but some of the X can be latent, something like that. So based on the type of Y here or type of X, there are lots of the advanced statistical method and advanced probability models. So for the first half of this lecture, I will discuss about these advanced models. So you will learn about many advanced statistical or econometric or sometimes probability models. And then based on your learning, I suggest you to think about which model can apply to your data. Right? Each of you will have a different data. So maybe you can first understand the feature of your data, and then you can consider which advanced models can be applied to your own PhD research. Okay, so this is the purpose of the first part. Okay. Okay, so today is we won't again. So I mean, the goal is normally we spend the time for the whole. Okay, so I will bring a briefly overview of the statistics and the probability. I think many of you already are very familiar with the issue, but today is just overview. So yeah, so maybe from next week and then more some advanced issue. Today is just the general models. Okay. So again, my part is about the probability and the statistics. So what is the probability? Probability is simply how likely something is to happen. So percentage, many times we use the percentage for probability. Okay? And the process of quantifying uncertainty, randomness, and fluctuation involved in the stochastic processes. And then statistics is a mathematical body of the science that pertain to the collection, analysis, interpretation, something, blah, blah, blah. Okay, so I don't need to explain detail about this, right? So, okay. And then the question, so, okay, so why you need to learn the statistical inference? Because our own approach mainly in engineering, our result is not only for the inference. I cannot say, of course, I cannot say all of your result is based on the statistical inference. But most of your work is based on the statistical inference. Why? Because we don't know the, how to say, the truth. We cannot observe everything, right? So we can observe only the part. Our data, all of the data cannot be perfect. For instance, when you experiment something, you may measure maybe something based on your major. But of course, we can only measure a part of it. So based on the observed values, we analyze and then discuss about some major findings. So in this case, your result is based on the statistical inference. So again, it's a real world, we cannot get the all information from the real world, so we normally collect the data. And then based on the data, as I showed, we just y equal fx, then estimate the parameters. And then of course there are some randomness and uncertainty, so we many times assume the distribution there. And then we calculate the probabilities, and then based on this probability, we have some information for decision making and design. Okay, so here, this is the general representation of the statistical inferences. So this is the real world population, the true information, normally we say. So in this case, we cannot get the whole information about the real world, so we sometimes get the random variable x. Why random? Because the variable itself is not perfect. So we assume, okay, the variable is random. Okay, so realize something, blah, 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 and then we normally present it as a probability function there, a certain distribution. Okay, and then for the distribution, normal distribution, log normal distribution, truncated normal distribution, whatever, we normally represent the distribution with the mean and the variance. Okay, and we can do some sampling, some experimental observations, survey or chemical experiments or whatever, or some getting some cleaning process in the big data, whatever. And then based on this, we can get the variables x there. And then sometimes we can get some representative based on the histogram there. And then we can get the mean and the variance also from there. So the difference is that here for the distribution, this is the continuous variable. But here on the right side here is more about the categorical variable. Okay. So categorical variable, continuous variable, it's okay, right? So I don't need to explain, right? So okay. Okay, then here, so this is the graphical representation of the another statistical inference there. So the process of the using data analysis to determine properties. So again, I mean, we cannot get the true data, the true information. So we only get the part of the information from there. And then based on this data, you analyze consistent with your own research purpose. Okay, and the data, then they get the probability, and then we assume based on the probability, we infer the true information. So this is the general academic process in engineering, especially in civil engineering domain. Okay. So here is more about the statistical application in transportation, consistent with my own expertise. And normally, I mean, generally, when we assume the statistical application, the classical issue is that how many samples are required and what confidence should I have in this estimate? estimate the model in the beta, for instance, in the regression model. And what statistical distribution best describe the observed data mathematically? So this is the quite common issue in any engineering domain. Okay. And then for the probability, we normally use the random variable. So I don't need to explain what is the random variable, why it should be random, right? So you know what is the word itself, right? Random variable, right? So I can pass it, right? Okay. So the random variables are devised to formalize description of event or postulate the computation of the probability. So random variable is random. Okay. So the variable can have a different value, the random variable. Okay. So and then some basic distributional terms. I think I'm sure you are familiar with this. The PDF, the probability density function. Okay, and the CDF, the cumulative distribution function. So maybe it's much easier. Is for instance, for this general most well-known distribution. Sorry, this is the PDF, probability density function. So this is quite a familiar distribution for everyone, normal. And then CDF means that calculate the area for each one. So it should be approached to 1. So this is the CDF. Okay. Okay, so PDF is a function used to describe likelihood the continuous random variable, and the function that describe probability randomness with something blah blah blah. So let's see a more detail. Probability density function is that for the continuous data. Okay, so for instance, annual profit of the MTR, some money, $1, $1.5, $2, whatever, something continuous value. Okay, so two conditions must be so fx means that probability. So probability should be, of course, the larger than 0 or equal to 0, right? It should be not negative. Okay, and then the integral of the PDF function should equal to 1 because the sum of the probability should be 1. Okay. So it's okay, right? This speed is okay. Okay. So does the probability of the value between something blah blah blah. So I think you should be very familiar with this. And the CDF is cumulative. The weight itself is already cumulative, the accumulated, right? The distribution function means that the cumulative probability for some value. So something until x, right? And then CDF is always the mean decreasing function because it's accumulated. So probability is added. Okay. And then CDF approach to 1 and x become large. Why? Because it's more value added. So you can see for this PDF, CDF is something like that. So it's increasing to 1. Okay, and for the PDF, the CDF is obtained by integrating fx between this limit to the x, blah blah blah. Okay. Okay, and the probability distribution. So many times, when you look at your data, sometimes the event means that the x are non-deterministic. Okay, so value can be some randomness or some uncertain, whatever. Okay, one can only describe such characteristics using probability distributions. Okay, so there are some two types of distributions based on the type of the variable. First one is the discrete probability distribution. So there are some binomial, geometric, and Poisson distribution there. And then also the continuous probability distribution. Negative exponential, uniform, normal, log-normal, something blah, blah, blah. Okay. So describe a distribution. There are two types of the statistical parameter that describe a distribution. So we have a different distribution here. Binomial, geometric, Poisson, and negative something uniform, normal, log-normal. So how to mathematically represent it using the statistical parameters, something like mean and the variance, right? This is the most common way. But based on the purpose of your research, we can use another one, of course. For the central tendency, instead of the mean, we can also use sometimes median. Okay, sometimes we can use the mode, and we can also use the quantifiers and whatever. And instead of the variance, we can use the standard deviation or range, whatever. Okay. So for the common statistical measure, of course, it's for the mean and variance. They are both commonly used. So how to calculate mean is that the sum of the value everything, and then divided by the number. So it's more like the average there. Okay, and the median, the 50% of the data point. So we normally the mean can be justified when we assume the distribution of the data, the value of the data, is the follows the normal distribution. But of course, in many times in real world, once you check your data, many times your value of the variable can be skewed. And then maybe your supervisor ask you to use the different index, like a median. Median is the 50% of the point. And then the mode is the most frequent observation. And sometimes quantile is the 25%, 50%, 75%, like a box plot. Okay. So once you look at the SCI papers in top journals in your field, each author use the different figures based on the different central tendency. Quartile, sometimes mode, and sometimes median. Especially when we assume the variables are follows the log normal distribution, we normally use the median instead of the mean because log normal distribution is the skewed left side. Okay, and also the measure of the dispersion. The first one is the variance. So variance, you can explain blah blah blah. So I don't need to explain the detail here. And then the standard deviation is the root of the variance, of course. And sometimes we can use the coefficient of variation. Okay? And then also, if the distribution is unclear, then many times we also use the range instead of the variance. Okay, so let's talk about one by one. The first example is the normal distribution. So normal distribution, I mean, it's quite common. So x is the something like that. Minus infinity to plus infinity there. Okay, and the commonly denoted, so m means the normal, and the mean, and the standard deviation. And the PDF, something like that. So this is also very common in mathematics, this PDF function. And then here, so log normal is the most commonly used in engineering field. So you can see based on the mean and the standard deviation, the shape is a little bit different, but basically all of them follow the Gaussian bell shape. Okay. And the standard normal distribution, the CDF of the standard normal distribution is the integral of the PDF there. And then we normally use the z value here, x minus 1 divided by the standard deviation there. Okay, then the standard normal distribution means that the mean is 0 and the standard deviation is 1. Okay, and then given any normal distribution here, the probability can be obtained from the standard normal probability taking this transformation. So it's a high school mathematics. Okay, so for instance, here this is the normal distribution, but we can make the observations to standardized for the better understanding of the data. So here, Z here means that if it is 6.2, it can move to this value based on the standard standardization, it can be transformed to the 0.1 to 0.12, sorry, and the mean become 0. So it's quite common technique here. And then cumulative standard normal distribution here. So it's same. I mean, for this standard deviation, we can just interval for the PDF over the standard normal distribution here. Okay, and then this is the how to we get the value from the standard normal distribution table. So I think you should learn from your bachelor or high school maybe. So I don't need to explain, right? Well, I can pass it. How you find the value, right? No. So is it too fast? I mean, I just need your feedback. It's okay, right? So yeah, today is the overview. So I mean, I can make it quickly. Okay. Okay. So based on this transformation, the standardization, we can transform to the standard normal table. We can get the value something like that here, 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 and so on. And then based on this value, we can calculate the CDF and then percentage of the area here, something like that. So maybe I can explain later more detail. So here are the probabilities for the certain area range here. So total area, the sum of the all the area should be equal to 1 because it's the probability. Sum of the probability should be equal to 1. 1 means the 100%, 100% means that should be happen. Right? And then here we are so many times talking about statistical significance. So as well as blah blah blah. Normally we use the 95%. So based on mean, within the plus minus 1.96, we say the value is the 95% significant. The value is the significant at the 95% statistical significance level, something blah blah blah. Okay. So here 1.9 here to here. It means that the area of all this area is 95% from the 100%. Most of them is here. Okay, so let's talking with a very simple example. So we have some data from the observation, and then we measure the speed of the cars on the expressway in Hong Kong or wherever. So we can get them. Okay, based on the distribution, something blah blah blah, and then it shows that mean is the 55, and the variance is the 7. Okay, sorry, the standard deviation is 7. And then what is the probability that the next observed speed will be between 55 and 65 miles per hour? And then to solve this question, we first based on this information, standardization, okay? And then this is the sigma, the standard deviation, and this is the mean. And the 50, 65 from here, and then mu, and the 75 is from here. And then it means that this one can be, can be transformed to the problem, and then between 0, 1.243. Same question. Okay, then we can, based on this table, value in this table, we can calculate the CDF formula there. So for here, CDF on table 1.43 is the 92%, 36%, 92.36%. And then for the F for 0 is the 50%. So if we calculate the difference between them is the 42%. Okay, so here we can answer what is the probability that the next observed speed will be between this area is that 42%. Okay. And the binary distribution is the more famous for the binary situation there. So it's the PDF is like that. So it's, if it is 0, then it's 1 minus P. And if it is 1, it's for P. Okay. So it's like a coin, the front side or the back side from the coin. When we, the turn of the, how to say, when you throw the coin, what is the probability to show the front side, or what is the probability to show the behind side, something like that. Okay, so the PDF for the Bernoulli distribution can be something like this. And then CDF for the Bernoulli function can be used for the integration of them and something blah, blah, blah. So this is the CDF function of the Bernoulli distribution. Also, geometric distribution here, you can see here the geometric function is more skewed in the left side. So sometimes your data is the skewed in the left side, then you can consider to use of the geometric distribution instead of the classical normal distribution. So this is the PDF and the CDF based on the integral of them. Okay, and the Poisson distribution is the discrete probability distribution. Is there anyone measuring the safety? Safety, no more. So this Poisson distribution is normally used in the safety area, the transport safety area. So Poisson distribution is the discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space if these events occur with a non-constant mean rate or independently of the time, rest something blah, blah, blah. Okay. So to summary, in your PDF, in your PhD work, these forward distributions are quite general. So if you find some good research issue, you may consider some advanced distribution proposed in the statistical society. For instance, I mean, the normal distribution, chi-square, exponential, these normal, these distributions are too common in the academics. So if you use this assumption in your model, it's okay, but it cannot be your contribution. But if you consider use some more advanced distribution, probability distribution for your research. For instance, I mean, the classical papers in your field, they assume the normal distribution. But you may find some logic why the normal distribution cannot be justified in some situations. Then you can consider some advanced distributions, something here. The Allen distribution, gamma distribution, some random distribution. Also, the I forgot the name, the distribution, something like that. So if you show them your assumption for the distribution is better fit for your own data in your PhD work, then it can be counted for your own research contribution. Okay, then maybe we can have a 10-minute break now, and then I will continue. Okay. Okay, I see. Thank you. Okay, I see. Yeah. This idea, it depends on some, I probably provide some examples why exactly this is. For instance, some of them may be easy, some of them maybe not easy to do. The assignment in your homework, so you can see page one, always in the class. So maybe page one, maybe announcing maybe next week. Because this week is the students can change the legislation. Yeah, so maybe that's some for instance, oh, yeah, this can pass on that. Yeah, no, thinking about knowledge. Something like this. You know how we can how the assignment is homework is very difficult. The key one will be yeah. Yes, this is the plan, initial plan. Reference. But reference, I will provide you. Oh, yeah. You don't need. Yeah. Just right now, what is the answer? So I can give you something like this example. So what is the problem? Yes, please. Yes, I will ask you. I think the context is set 1 hour, and I can provide you 1.5 hours. It depends on if you finish earlier than you.
对，这是简约传承的，这个是也非常清楚的，没有科学的问题吧？啊，对，我是的。
All the
There's no door between this group, but you have a door. And other things.
Okay, so let's start the second session. So next topic is about the sampling issue there. So sample size determination. So again, I mean, the population here is that the real world, the perfect information. But for the researchers, we cannot observe, we cannot assess the perfect information, all the information. So we normally use the sample and then analyze it using some statistical models. Then based on the result, we infer the whole population. Then we can make some conclusion based on our own research. So this is the general process in the engineering studies. But here, the problem is that how we can decide the sample. For instance, if we do some environmental engineering or chemical engineering, I can imagine you normally get the data from the experiment in your lab, right? Then questions. So I don't know, of course, in detail, but the question could be that how many times you measure the experiments, right? So of course, I mean, you can do for instance, 1 million times. You can measure 1 million times. Then maybe it could be more quality information, but it requires too many resources. Too many resources means that you spend lots of time to conduct the experiment 1 million times, right? So considering that you should publish many publications in polio, so actually it's not good approach, right? But if it is too small, you can just get the data just from the 10 times. Probably it's possible, but it won't do the job. I mean, the means that the conclusion, we cannot trust the conclusion. right? So what the researchers want to do is that we should find some balance with the academic justification. So naming justification is very important for your academic paper. Okay. So how many for the sample size? How many observations we need? Actually, no answer. No correct answer. Don't say what should we do. Okay. But because it depends on the several factors, like a confidence bound and the standard deviation and the tolerance, whatever. And also you should consider the externalities, whatever. But although we know the larger samples is better, I mean better estimate the beta. As the size, for instance, when we estimate the model, this is the true value. We say this is the true value, true parameters. But what we get it is the estimated value. We assume that this is the unbiased estimate of the true value here between them. So of course, I mean, if the sample size is much bigger and bigger, then this relationship, this estimation result is close to the true value. But if the sample size is small, they can be different. Okay, so in these aspects, so normally large sample is helpful, but it is more expensive, right? You may need more your time, even though you may need more devices for your experiments sometimes. So usually only able to measure a fraction of the possible values in the population. So for instance, in the transportation domain, Hong Kong government officially they survey for the household, the travel characteristics. It's called the CTS in Hong Kong. Once in 10 years. Why? I mean, for instance, once in every year would be better, of course. But why why Hong Kong governments do once in 10 years? It's very expensive. They should hire the people, and then they should spend lots of time. So everything is about the money. Okay, even the local population is about 7.5 billion people living in Hong Kong. The government official survey, they only survey people 30,000. So it's only of around 1% of the whole population. So someone can say, of course, we can do some 10 times more. Of course, it's better. But why they didn't do is expensive, right? So we should consider the constraint. Okay, so therefore we will want to collect only as much data that will give us the required level of the statistical confidence. So to justify our sample size, we normally use the statistical confidence. This is the most general way to justify our small sample. Okay. So how to do is that this is the general equation of the minimum sample size. So the n is the minimum number of sample, and the S here is the estimated sample standard deviation. And the Z value, you know what is the Z value is from the first session. Okay. And the error is the permitted error in the average sample. So you can see the error, as error is bigger, size of the n will be lower, right? So bigger sample size n means that they will have a lower permitted error. So it's much better for the true information. Okay. So here, I want to collect the speed. For this is an example. We want to collect the speed data from the freeway segment. And the previous studies, we already know that the standard deviation S equal to 4. And the 1 to estimate population mean, we need the plus minus 1%. 1 kilometer per hour at the 99.5% confidence level. And then if you see this example, and then you can calculate the minimum sample size. So this is the S value is here. This is the epsilon error plus minus 1. And this is the Z value for the 99% is the 2.58. So we can calculate just mathematically. Then we can say that, okay, so for the round node here, and then we can say that for this example, the minimum sample size statistically can be justified is the 107 observation. So in this way, when you write in your paper, you can justify your decision about the sample size. Okay. So it's fine. And then for the sample accuracy, maybe it's also common with you. I mean, for the confidence, how much confidence can we have in our estimation? Sorry. So U is here, the true population mean, and X is the sample mean, and S means the estimated sample standard deviation, and M is the sample size, and the Z value here. So based on this information, again, so 1.96 is the 95%. So we normally use the 1.96 value most commonly in statistics. Why? Because it shows the 75% confidence level. 75 confidence level is that this area, sorry, the area with 1.96 is the 95%. And this part is 2.5 and 2.5. So you may run it in your high school, right? Okay. Okay, so in this example, we can also solve some mathematical problem. So n equals 54, and average is the 47.8 kilometer per hour, and S is the 7.80. And what are the 95 confidence interval there? Then we can calculate mathematics here, 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 and then minus plus will be different. So I assume you are already very familiar with this equation already, maybe in your high school bachelor. So I will just quickly pass it. Okay, so and then remaining thing is just a mathematical calculation. Okay, so in this way, we can say that in this example, the 95% confidence interval for this average and the standard deviation with the sample size is the between the 45.7 to 49.9. Okay. So I think it's not difficult, right? Should I explain more detail? How do you think? I mean, for instance, because today is overview, so I normally prepare the example for master level or maybe bachelor level. So I think I don't need to explain detail why should be there and why should be there, right? So I will see, okay? So okay, then next two issues about the hypothesis testing. Okay, so what is the hypothesis testing? Is that the hypothesis testing is the procedure based on the sample evidence. So use the probability theory to determine whether the hypothesis is a reasonable statement, and the unreasonable then should be rejected. So for instance, what is the general for this one? So, okay, so here, regression, you know the regression model, right? Regression, very common. So in this case, when you apply or analyze your data using the regression, we have some beta there, right? Beta 0, beta 1, beta 2, blah, 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 right? Then for the statistical perspective, what is the next question? Can we believe this value? Right? This value is significant enough, something like that. Otherwise, we don't need to use the regression model, right? So in this case, to answer, okay, based on the statistical analysis for your data, for your reports, we have some beta estimation result. So is it statistically insignificant enough or not? So to answer this question, we need to do a hypothesis test. Okay. So here's the another example there. So we have a before and after study. We measure the speed of the car, and then the speed reduction of the 5 mile per hour, and the accident reduction is the 10%. And then we will compare the two distribution. So and then the weather observed pattern data feed of a particular distribution, something like a chi-square test. I will explain more detail later. And the differences between two or more group ones and values, and the test of the independence between factors and different in proportions, and significance of the coefficient in the regression model. I explained that. Okay, something like that, and the significance of the overall regression model, and so on. So I will show you one by one. So here, on the example, estimate the population mean age using the sample mean age. So hypothesis testing. Test the claim that population mean age is 50. Okay, so this is the hypothesis. So here we need to draw the conclusions and we're making decisions concerning the population based on the sample result. So it means that here. So based on the estimation result of your sample, we infer the status in population. Okay, so here, and then here assume population mean is 50. So H0, H1, I assume you're familiar with it. So H0 is the mean equal to 50, and is X is 20. Likely if you move equal to 50. And then not likely is rejected. So we can clearly, for this simple example, we can clearly decide whether it is rejected or accepted. But if there are so many observations, then it could be questionable. So for instance, here, we need to do the answer about it. So we first need to establish a null and alternative hypothesis H0 and H1. And then we specify level of the significance. And then based on the sampling distribution, construct the critical regions and the critical values. And then we can compute the sample statistics and we decide whether or not to reject the H0. Okay, so for instance, this is called a one-tail problem. So if we propose a hypothesis that the average travel time from Hong Kong Island to Kowloon using the car is more than 30 minutes, and the alternative hypothesis is less than 30 minutes. And then this is the H0 null hypothesis, and this is the H1. So here we can see the mean hypothesis, alternative hypothesis is just in one direction. It's only about the minimum, not about the maximum. So we can say this is the one-tail problem. And then let's assume alpha is the 0.05. It means that 95% statistical significance level. And then we are testing the population mean travel time against the constant. The test follows a standard normal distribution. So here we can only calculate the critical value alpha here. So it means that alpha is 0.05 means that this area is the 5%. It means that this area is the 95%. Because the sum of the whole area should be equal to 100%. Okay. Then the critical value is something blah blah blah, and then you can see find the value for the 95%. In the table is the 1.2645. So this is because this is the one-tail problem. So you may experience about this, right? To find the Z value, no, it can be no. You know what is the process? From the Z table, you know how to find the value, Z value, based on your proposed, right? Is there anyone doesn't learn about this before? I think everyone learned in your high school or bachelor, right? Or your master, I think, I'm sure, right? Okay, yeah. Okay, so here, then next example is a sample. Okay, so we have a different sample. Something like 1, 2, 5, 6, 7, 8, 9, 10, and 20 observations there. Sorry, 16 observations there. And then when you calculate it, and the mean is the 27.93, and the standard deviation is 5.46. And then based on this information, we can calculate the z value, right? This is the sample size, the square of the sample size, and this is the mean here, mean divided by the H0, and the standard deviation here, right? The definition of Z. Definition of Z here, right? So based on this way, you can calculate the value, Z value for this example. Example as a minus 1.52. And then based on the information of the 95% 0.005 for alpha, it should be minus 1.645. So then we can see this value is bigger than minus 1.645. So we can say we cannot reject the null hypothesis. Okay. And then the next one is about the distribution fitting. So it's about the question, how do we determine the distributional form, and how confident can I be that the sample distribution represents the population distribution? Okay. And also the plot data, we can use the histogram or examine some plot, box plot or whatever, and we can rely on the theoretical distributions for comparison and so on. So here, it's about the histogram. I think many of you, especially once you use the data based on the some lab experiment, maybe normally you use the histogram to show the property of your data. Also, could be so be if the distributions look like a match and proceed to a statistic, we can test some statistical test. And it's about the different tests having this device to compare fit of the empirical data with the theoretical distribution. So most of the common is the chi-square test. Okay. So what is the chi-square test? Chi-square test is for the define the categorical variables and assign data to the categories. So once your data is about the categorical variable, then you can conduct some chi-square test there. But of course, there should be at least 5 data entries per category. And then you can compute the expected number of the samples for each category based on the theorized distribution and compute the difference between the actual observations class and the theoretical blah, blah, blah. So I can play with you some example there. So this is the chi-square value, and the n is the observed number of some category variable, frequency of the observations, and so on. And the f is the theoretical frequency or expected observations there. And I is the category index, and the k is number of the categories, and so on. Blah blah blah. So this is another example. So this is a more common example about the memory. So let's assume the 3-digit number made by drawing a digit between 0 and 9 from each 3 different containers. So we can focus the draws from the first container. If the number is randomly selected, each value would be equally likely to occur. So it's like a card game. We have a 0 to 9, any number on the card. And then randomly, we try to pick up one of them. And then we conduct this 500 times. And then we can see the number picked 0 is 48 times, 50 times, 55 times, blah, blah, blah. So the sum of them is 500. And then the average is 50. Okay. And then here, we assume we can also make some hypothetical test. So random draws follow a uniform distribution. Uniform distribution means that all the number of them are exactly equal. But of course, in reality, it's not exactly equal. So the question is that in this situation, this blue, the blue graph, can we say this is statistically same with the uniform distribution there as a red line? So to answer this question, we can conduct the chi-square test. Okay. So, here the number is 10. So the probability for each one is the 10%. Okay. And then of course it's the 95% significant level. And then the degree of the freedom should be k minus 1. K is here is 10 because 0, 1, 2, 3, 4, 5, 6, 9. And then degree of freedom is 9, and then significance level is 95%. And then in this case, when we look at the chi-square distribution table, you can find a value 0 is the 95% significant level with the freedom is 9, and then you can see, oh, this is the critical value of the chi-square. Is the 16.92. Okay, and then here we can compute the chi-square value, like sum of the categories, expected value, and then observed value divided by expected value square. Okay, then you can compare them. The value is the 6.04. And then here we can say 6.4 is the lower than 16.92. So it means that we cannot reject the null hypothesis. So it means that we cannot reject that the random rules follow a uniform distribution. Okay. And then so we can say this value, this distribution, categorical distribution, we can say this is the statistically same with the uniform distribution at the 95% significance level. And another example there, stop sign observation study. And then we observed some stop sign studies are performed before and after an intensive enforcement campaign, and results are summarized below, and determine whether the difference in stop sign observed after the campaign was statistical significance at the 5% level of the significance. So something like that here, before, after, total. So we just count, this is the count information there. And then based on difference, we can say that from the before and after, there are no difference between them in our data. And then H1 is the alternative hypothesis, means that they are different. And also the 95% significance level. And then we can calculate the degree of the freedom, and then it's equal to 2. And then from the distribution table, chi-square is the 2 and 95%. 2 and 95% is the 5.991. So this is the criteria to decide whether to reject the null hypothesis or not. And then based on the computation here, we can get the chi-square value 6.8. And then the conclusion is that this value is obviously larger than this one, so we can reject the AC0. It means that the before and after the campaign, the distribution are statistically different. Okay. So before I go to the regression model, some of the examples like this, how to say, for your evaluation, like a quiz and assignment. Of course, I cannot say everything is that, but one or two questions, something like very easy like this. Okay, based on the example. So I will ask you something similar context, and then I will give you some table there, the data. Then I will ask you, can you reject the whole hypothesis or not? Can you say they are different statistically or not? It's a very, very basic question, but it's for the point for you. Okay. Okay. So, any questions so far? Any feedback or question? Whatever. Okay. Okay. Before regression model. So, for this class, I mean, I was because this is the first time. I mean, this class is the first time this semester. So we designed the course. I mean, from the fundamentally view. So when I prepared this course, I was asked from university to make it a little bit more difficult. But yes, I mean, it's possible. But the point is that if I make it very difficult, then it requires you spending more time. But in my perspective for PhD students, I mean, it's better, more better, I mean, to focus on your own research. I mean, so I'm thinking how to organize it. So maybe I can provide some broader knowledge about some statistical models, but maybe the calculations are not much deep. Then maybe it can be useful information for you, maybe. But it's for the my part. I mean, the second part for the machine learning. I don't know how the professor prepared it. So I'm just thinking. So maybe from week 2, I will explain some advanced method. But for the evaluation, maybe I will ask you not much deep calculations. Maybe if this is my plan, so I didn't decide yet. Okay. Okay, so let's continue about the regression model. So regression, I mean, it's quite common. So even Googling, you so for instance here, how to say? So far, I explained some basic interpretation or basic test about the data. But the point is that here, when we talk about the data is very simple, right? So you can see here, very simple. Also, this one was very simple. So we are now talking about very simple data. But of course, I mean, at the PhD level for your study, the data will be very complex. So more information, more variable, and multinomial variables, and then more complex relationship between the variable and so on. So in this case, I mean, in terms of the statistics and probability, the starting point for your research at the PhD level could be the regression analysis. So regression analysis is something like that. So here, this is the observation from your data. And then we can make a line, the best line, to best explain about your observation. But of course, this is the two-dimensional relationship. So only single y and single x. But normally in your data, you have a single y and then multiple x. So it's a multi-dimension. Okay? So in this case, there are lots of the statistical issue. Can we have to use the simple regression model there or not? But only no. Okay. So today, I will of course start from the simple regression model. So here, simple regression, only one independent variable, and then multiple regression with a multi-value. Here, independent value is x, right? The x there, okay. And then random trees is f. So here, in this case, for instance, this is the y in your from your data, and this is the x, and the f is the statistical model. Okay, and the three predictors need to be independent. Yeah, so. And then we can consider many kind of the factors, personal, something general, something blah 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 blah, based on your own research. Okay. So here, this is just an example, but here, as I present there, so we have some y, and then there's x there. And then based on this relationship, we can estimate these parameters, right? This is the general idea for the regression model. So here, we estimate the model, blah, 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 and then, I mean, even using Excel, we estimate the regression model. Here, and then the logic of the regression, what is the, for instance, here, what is the best line? For instance, we can draw the line somewhere here, and then somewhere here. Then how we know this orange line is the best? What is the logic there? Mathematical logic there is that we calculate the difference error. For this, so this is the y, and this is the x, and then this is the observation, and then for this x, right? And then this is the estimation, estimated value for this x, right? And then we calculate the difference there between the observation and estimation, and then based on this value, we square, and then sum of them for the all observations, and then maybe I explain. Maybe not yet. So here we say for every I, y I, sorry, y I at, sorry, it's absolute, and the square, and then the beta to make a minimum, this is summation. Then we say this beta is the optimized value. So based on this one, we can calculate the beta 0 and the beta 1 here. So this is the general logic how we optimize the beta, the parameters. So here, this one, SSE. So this one, this is the logic how we can get the beta. Yeah. SSE, and the regression model. So this is the algorithm how to calculate the how to estimate the beta here. Something blah blah blah. So here, then let's play with another example. So when we use planner, observe in the 5 zones of the city, the number of the gas stations y in the relationship to population x of the intent was as follows, something blah blah blah. This is the observation in your data set. And then we can set up the linear regression model y equal b0 plus b1 multiply x. And then we can determine the b0 and the b1. Okay, so this is the question. Then, based on this equation, we can calculate. We can calculate the value for the covariance and values of the x and the covariance of the xy and something blah blah blah, and then we can get this value, optimize the value. This process is for the minimizing this in the regression, general regression model. So this is normally the estimation. So if you wonder more about this process, how to optimize it, you may also take the another course in CEE, I forgot the full name, optimization course. Then Professor Anthony Chen will explain the detail how to do. Okay, so to avoid the overlap, so I will not discuss too much about it in this class. Okay. Okay, so how we calculate? Do we calculate by hand or manually use some software? Even for the simple data, the Excel can solve the regression model. So we can put there, then they estimate the parameters here. Okay, so this is the how to do, use the Excel. Maybe. Maybe I can continue without break time, and then I will finish it today a little bit earlier. Okay, I think it's much better to do. Okay. Okay, so for the estimation of the regression model, this is the basic approach how to do, and then the Excel is blah blah blah. And then the geometry of the regression model, we calculate the difference between the observed value and the estimated value, and we sum of their different square of the difference, and we try to minimize it, blah blah blah. And then for the regression model, we have several definitions. Sum of the square total called SST, and the sum of the squares regression SSR. So the SST, observed value is about the sample mean, and the SSR is about the estimated values about the sample mean variation, captured by or explained by the rules explanatory variable. And the sum of the square error, SSE, means the error term, minimize the OLS there. So, okay, so here, maybe I can put here. So for the regression model is quite common. So once you have the data, any data, blah blah blah, then you can blah blah blah, and then you can get the estimated beta there. So as I explained you, the first question in this regression model. So our first example is that first concern is that so the estimated beta is statistically valid or not. So even the estimation result, it can be insignificant, right? So in this case, we want to know whether these values are statistically significant enough or not. And then the next one. So this one is about each parameter. So the result is a combination of them, right? Then that's the question. So the combination of the estimated value, they statistically will explain my data or not. This is the second question. So first question about the beta is about the individual separated question for each beta. It can be significant, it can be insignificant, it can be significant, and so on. But the second question is about the betas. So is it enough then? It's more about the model fit. Model fit means that this model is well fit to my data. Okay, so this is another significant issue. So here, the lecture file talking about the model fit, or is also called the goodness of fit. So here, this is normally we use the R square to discuss about the model fit. Have you heard about the R square before? Right? Okay, it's okay. So R square should be between 0 and 1. And then if close to the 1, the value of the R square is close to 1, we say the model fit is good. If the R square is close to 0, then the model fit is not good. Okay? So here, this is the how to calculate the R square, but normally we can get the information from here. Here. So normally in these days, many software, they automatically give us the R square. Okay. So R square, if it is in here, then and then next question, what is the value? Okay, so by R square, for instance, here, 0.65, is it good or not? So actually, there are no clear threshold. Okay, so someone say, oh, this value is too low, and then it's not good. Or someone say it's too high, so it's okay. So no one knows. But normally, what in the academics, we say if it is in between this value, 0.2 and 0.4, then it's good enough. If your model fit in your data is lower than 0.2, then it can be questionable. But if your model fit on your data based on the regression model is lower than 0.1, something like 0.00, for instance, 0.061, something like that, lower than 0.1, then if you this result in your paper, then the reviewer, I'm sure they will point out this issue. I cannot trust your result because the model fit is too low, so your findings cannot be justified, something like that. Okay, but in this example, it's only 0.65, so model fit is already quite good. In this example, we can say. Okay, and then another issue is adjusted R square. Maybe I can explain next week about this adjusted issue. So here, adjusted R square means that the R square has a tendency that as we use lower parameters, for instance, so same data, we have new information, but sometimes for the x, for the first regression, we can only 10x here. The second regression, we can use the 5x there, right? So we can estimate the different regression model based on your data. How many variables you included, you can choose some of the significant variable. So we can test what is the best model. So one the weakness in the definition of the R square is that as we use the more x, as we estimate the more parameters, then the R square is increasing. So it means that we need to use the more and more variable is always better based on the R square, but it's not true. So I will introduce you in week 3. So we have another definition called the adjusted R square. Adjusted R square means that it gives some penalty for the regression model who use the lower number of parameters. So I will explain the week 3, okay? And then here, so based on this one, so okay, so this is the how to calculate the R square, something blah blah blah, then so blah blah blah, and here. So here, this one can be with the simple correlation, Pearson correlation way. We can transform the equation like this. And here, okay, so let's talking about the next example. So a land use planner observed the 5 zones of the city. The number of the disease stations, this is the Y, the dependent variable in relation to the population X. In the 10,000 was the S12, something blah, blah, blah. So the question is that determine the SQL there. Okay, and then based on this, we can calculate the equation. Maybe if I make it for your equation, then I will provide this equation. Okay, so you can just match what it means and what it means. So you don't need to remember everything, every equation. Okay. So here, in this way, you can watch them calculating, and then this is the square. And then you can divide it down to the end, then you can get the final value 0.65 here. Okay, so this is the how to work in the regression model. And then also we can also the about the another test to analyze their variance. So this is the regression, the sum of the squares for the regression, sum of the squares for the errors, and the sum of the squares for the total, and the DF and the mean the standard deviation, blah blah blah, and then we can get the F ratio here. And then equivalent with the ratio, we can blah 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 blah. Okay, so if we know the R, we can get this F ratio based on the calculation. Okay, so let's play with the example. So here, same question here. And then I can ask you a very simple statistical question, calculate the alpha and the F ratio. Okay, so this is the relation to calculate the F ratio. And then F can be calculated based on the simple equations using the concept of the R square there. So since we already have the R square 0.65, we can calculate the F value very quickly. Here, 5.57. And then we can compare the F value, and then we can conduct the significance there. Okay. And then for the significance of the regression efficient, so the errors of the blah blah blah, and then the T value. Have you heard about T value, right? It can be known T value in the regression model, maybe no. Ah, okay. So how to say? So to answer the first question, so the beta are statistically significant enough. So we have two types of the information. One is the so for instance, let's say beta for the beta 0, the regression model estimated minus 1.0, just for example. And then with this information, we have another concept, standard error. Okay, standard error means that here, standard error concept is here. So beta 1 is the beta there, and then the SY is XX is a standard deviation, means that the two XE for the XY. So standard error means that how much error can occur to decide this value, the minus 1.0 there. Okay, so based on this value, they can calculate the standard error. So maybe this is the relation to week 3. I will explain in more detail about what is the standard error, what it means statistically, and so on. Okay, so just today, let know that this is the way how to calculate the standard error. So maybe it's out of scope today, But based on the T distribution, definition of the T distribution, we can calculate the T value, the beta 0 value divided by standard error. This is the definition of the T value. So here, for instance, standard error is what can we say? Because this is the error, so it should be non-negative error because error is always positive or 0, right? And then error could be 0.5. Then in this case, the T value for the beta 0 is the so -2 can be the T value for this beta 0. So I will explain the week 3. Okay, I will explain the detail about the regression model in week 3. Okay. So in this case, to decide the value, here we can calculate the T value. T value for the each parameters. So based on this T value, we decide whether these values are statistically significant or not. So as you see in this table, so the absolute value T is larger than 1.96. So you know what is the 1.96, right? The 95%. So we can say that the value, the estimated value is statistically significant at the 95% significance level. So this is the interpretation of the result of the regression model. Okay, so maybe I can show you example, maybe not today. So for the left example, so here also same, and then determine T ratio for the B1 there. Okay, so here we have the SB here and the B1 1.3. So we can calculate the T value for the B1, something like that here. Okay. And then also for the B1 S1 and so on. So on here, for the test, we say the null hypothesis is that so the question, okay, can we believe this B? So if instead, if we cannot believe what, if we cannot believe this value is equal to 0. So if everything is 0, then y equal to 0. So nothing. Right? So in this case, the null hypothesis is that the parameter is equal to 0. Okay. So alternative hypothesis, of course, the estimated parameter P1 is not equal to 0. Okay. So here we can calculate the T value. I forgot to explain it. So here, actually here, it's a -1 is missing there. Okay. So the minus 0 is nothing. So T value is the same to the -2 there. So here, 5% something that B1 is some error. So we know this value here is the 1.96 there, right? So and then we can test there. Maybe for this one, I can more detail explain in week 3 about the regression. Maybe it's out of scope today, maybe. So I mean, I will explain more detail about this in the week 3 because week 3 is about the fully specific about the linear regression model. So I will explain you how to design it and how to calculate it more detail. Okay. So any question for today? Is it too difficult? How is it? How do you think today? Because today is the overview, so I quickly thinking about the statistical issues very quickly, but is it how to say, is it too easy or is it too difficult? How do you think at this level? Can you give me some feedback? It should be more difficult or
No. Okay.
it's okay. I see. So for the next week, I will introduce you some more advanced models, but the level of the difficulty may be similar with this level. Okay, not much deep. Okay, not much complex.
Yes.
Okay.
Okay.
Any more feedback? Oh,
I would say I understood all those parameters or method, but I just only understand it. I read it in the papers, other people's work, but I never used it. I know the meaning of it. So I think we better slow down a little bit.
okay, so the
Future.
okay, I'm seeing this.
That.
Okay, so I will read this one and then it's okay. Okay, and also any other feedback? And okay, then it's okay. So tomorrow, sorry, not tomorrow. For the next week, the topic will be about the probability and the statistical inference. I mean, the frame itself is similar to today, but the context will be more advanced issue compared to the general topics. Okay, and then maybe I can talk with you more slowly and some more example. Okay, okay. So thanks for today, and then yeah, see you next week. Yes. Yeah. Kind of. So, for instance, here, something like that. I will let you.
I'll tell you.
Yes. Here we have a black hole. So maybe you are not registered. You need to ask Geo. Not Geo. Which department? Maybe you ask the Geo to make sure. Yes. Because it's not out of my control. It's not my authority. So, but maybe next week there are some changes. Maybe. Oh, I cannot control it. Yeah, so the university decide the classroom and. Maybe. Sorry, I have no power. Yeah, I feel this also. I don't know why. Yeah. Indeed. Thank you. And you can smell. So you mean the in advance means that a few days more?
Yeah.
I will try my best. Yeah.
Sorry, it is a situation that you haven't all the just finished all of it.
I have the initial materials, but I should make it more better. Yes. Because this class is the new in this semester.
Oh.
Yeah, this is my first time to teach this course.
Oh, really?
Yeah.
So I also make some how to say, or adjust the difficulty, and then some moderate some topics. I mean, considering the feedback of the students. Yeah, but I will upload it as soon as possible. As soon as possible, I can do it.
Because even though we heard that things actually
So it's not easy.
I can recall that
Ah,
you asked me the question.
Okay. Because for instance, I mean, for the today lecture 5, I discussed with the GO and the other professors to be allowed, but they advised me because it's overview, so it can be easier, but I should make it much difficult because the PhD students, they have very good ability, so I should make it difficult. So okay, I mean, but I understand the situation, so maybe the next week will be much better. Yeah. Other question?
What one get the gender?
Then
Agenda.
agenda.
What it can, okay, I could be.
Oh,
So, here, we have a actual platform.
Ah.
Lab. Have you upload
only.
as something is the platform?
What? Is it on the platform, right? But are you sure you registered in this course?
Yeah, but,
Maybe. Because I uploaded yesterday, so it should be there.
If other can also do it.
Oh, yes. A, to Thomas.
Yeah.
so what's different? Okay, B is taught by another.
I'm not sure what it is, but A means the this semester.
Okay.
Yes.
Oh, got it.
Oh, right. Okay. Oh, yeah. Okay. Yeah.
We upload the recording to the lecture.
Yeah, I mean.
Yes. Some mathematical problem. So yeah. So something like example today lecture 5. Something like that. I can give you some example, and then I will ask you to bring your calculator. Oh, yeah. And then maybe because it's PhD course, so maybe I will provide you some, say, the table of the formulations there, and then if you need, then you can find it in the appendix.
Right.
Okay. Yeah.
So this called many instances about different capital model.
Yes.
Okay. About fish engineering.
So sorry.
Fish engineering. Yeah, like
I don't know the name.
it's just like my recent topic is about image analysis. So I need to turn the image into so there's some method to get different kinds of features. Yeah, something like that. Because only using machine learning models sometimes cannot get good results. We need to turn the feature into
Maybe in my part, maybe